Continuing with the homework questions from Unit 6. This one is another optimization problem. We've got page 152, number 15. And this is similar to one from the lesson. So we want to determine the level of sales that will maximize profits. So what I'm looking for is a function for profit. Maybe I won't use that function notation because I don't have a variable yet. But in general, the profit function is going to be the revenue minus the cost. And what we're going to have here is that the revenue is going to be the price times the number sold. So just kind of making a note maybe up here. So revenue is the price times the number sold. So my profit function is going to be the price function. So that 2,000 minus 5x times how many, what are we doing, computers you're selling, minus the cost function. So this is that 15 million plus 1,800,000. Hope I'm getting the right number of zeros, plus 75x squared. So that's my function for my profit. And this would be negative 5x squared plus 2,000x minus 15 million. Minus 1,800,000 x minus 75x squared, and then that would be negative 80x squared minus I don't want to miss my number of zeros here, so I'd have 1,798,000 x minus 15 million, and that 15 million is just going to go away because we're going to take the derivative here. So the derivative is going to be negative 160x minus 1,798,000. So we want to find where the derivative equals 0. So that's going to be 160. Sorry, I stopped this because I realized I made a mistake. Let me highlight, and maybe this is what went wrong for you guys if you didn't get this question. I missed that. It's X 1,000 units. So they will sell, the number of units they'll sell is 1,000 times that. So this has to be in here 1,000x. So they're going to sell 1,000 times whatever that x is, and that's going to be the price. So I needed to have a 1,000 in there, which is going to really change things in terms of my expression for my profit, because I was getting like a negative number of sales when I went to solve that, and I thought that cannot be right. So I'm just going to skip to the simplified, FOIL that 1,000x in, and collect your like terms. The profit function would be, so if I simplify this and write it out, I get negative 5,075x squared plus 200,000x, and then plus or minus at the end that same 15 million. keep the lines separate. So then I will get a different derivative. The derivative is going to be negative 10,150x plus 200,000. So where I'm looking for the derivative equaling 0, I get 10,150x equals 200,000, which does not get me a negative number for x, which is great. So x is 19, and because x is like the number of thousands, I'm going to keep 3 decimals here. So it's 19.704, but I want to multiply that by 1,000 to say that that's how many bikes or computers I would need to sell to maximize profits. And again, you could double check between, say, 0 and 19.704 and between 19.704 and infinity all the way up, the derivative of profit is going to be, this is going to be positive for x values less than that 19. So that's a positive derivative, and what that tells us about the function is that it's increasing. If you put in a bigger number than 19 in here to the derivative, this would be negative, bigger negative than that. So you get a negative derivative, then it's decreasing. So that shows us that we have a max there. Because I don't actually have an endpoint. I assume I can't make negative computers, but it would just be greater than 0. We don't have like an upper bound. So we could say, therefore, maximum profit if you, does it ask how many we should make, sell 19,704 computers. So I had a couple extra slides in here just from doing some other homework questions, and then we have some on the related rates. Okay, so the first one, we're given this function, and we want to figure out how fast is the perceived temperature changing when the person is 5 meters away. So I'm going to rewrite this T at x equals, I think that this is easier to do the derivative of if it's written as a chain rule question, but you might feel otherwise. And what I'm looking for is dt, which is, sounds kind of terrible, but this big T is temperature, and that's in terms of time. So I don't know what that is. And I'm not actually going to need the what the temperature perception is, but I could figure out what T at 5 was if I felt like that was, if I did end up needing that. I'm also going to have the x, which is your distance from fire. So we know x is 5, and we know that the person is moving away, so dx dt, I don't know why I'm writing the derivatives on the top, is moving away at 2 meters per second. And it's important always, especially with those rates of change, to think about the sign. Now, if they're moving away, that means that the distance from the person to the fire is increasing. So if the distance is increasing, that's a positive rate of change. That is a positive 2 in there. So it's 5 meters and 2 meters per second. So when I take the derivative of this, dt by d little t, change in temperature over the change in time, will be negative 200, 1 plus x squared to the exponent negative 2. This is just chain rule here. Now when I do the derivative of the inside stuff, I know that x is a function of time because the person is moving. So then I'd have the derivative of the inside stuff, which is 2x, and then the rate of change of that x function, because x is not just a variable here, it's a function of time. So dx dt. I'm just going to throw the numbers that I know. I know x is 5, I know dx dt is 2, and that will give me the change in temperature over change in time here. So I've got negative 200, 1 plus 5 squared to the exponent negative 2 times 2 times 5 times 2. Just kind of being careful that this would be like negative 200. Just when you're typing this in on your calculator, which things are going to stay on the top and which ones are going on the bottom. 1 plus 5 is 26 squared on the denominator. But if you just did the negative exponents, that would work out just fine as well. So I get that this would be negative 5.9, and then that's going to be, thinking about our units here, this is the change in temperature over the change in time. So this is degrees Celsius per, and how fast is the person moving? Per second. So as they're moving away, it's decreasing, the temperature sensation that they're feeling is going down by about 6 degrees Celsius. Okay, so the next one is going to, at first glance, I kind of think that this might be able to be done with trigonometry, but I don't think that that's how most people would do this. I think similar triangles is probably more likely and actually would work out fine as well. So if I take a look at this, when this man is standing 1 meter from a lamppost, his shadow is 1.2 meters long. So there's a light there, and there's somebody standing there, and when this is 1 meter, the shadow on the ground is 1.2 meters. And we know that the man is 1.8 meters tall. So the light coming from the lamppost is making the shadow out there. And what we're going to need to know, what we're not given, but we can figure out, is what's the height of that lamppost, because that's going to be something that's constant. So that's going to be an important thing for us to know. So here, I would take a look at this in terms of a similar triangle. So that would be 1, 1.2, 1.8, and let's call that H. So if we looked at the big triangle here, we'd have H and 2.2. And if we look at the little triangle, that's 1.8 and 1.2. So we could say that H over 2.2 equals 1.8 over 1.2. And then we can cross multiply and figure out what the height of that lamppost is, which will just be a constant for the whole question. So H equals, is it going to be nice? Oh, it's a nice number, 3.3 meters. So the height of the lamppost is going to be 3.3 meters, and that's going to obviously not change through the whole question. Now, we want to kind of set up what our related rates are and what is happening. We know, and also the man's height's not going to change either. So we've got this lamppost, that's 3.3 meters, and we have a man walking, and he is 1.8 meters. Now, we want to figure out how is the shadow, the length of the shadow changing. So if I kind of draw the light down here, and I want to sort of talk about the two things that are changing, and that would be how far away he is from the lamppost and how long his shadow is. So I might say let X be distance from the light and let Y be his shadow. So I'm going to label in an X there and a Y. Now I know that we could figure this out, like how long is his shadow at that certain time. And we could also figure out what the rates of change are. So I know this is asking, oh, they don't even tell us how far away it is. Okay, so the man is walking away at 120 meters per minute. So I am going to want to figure out X and dx dt. That's the distance, the speed he's walking away. So that's 120 meters per minute. And Y would be, we'll figure that out, and dy dt. So those are the things that I'm going to want to know. Now, first of all, this is kind of tricky because they say 5 seconds, but they tell us he's walking 120 meters per minute. So 5 seconds is, if I do 5 divided by 60, or it's 1/12 of a minute. So I want to figure out how far he has gone in 5 seconds. So if he walks 120 meters in a minute, 5 over 60 would be 1/12 times 120, which is 10 meters. And I'm going to assume that that means he walks away starting from this 1 meter. So his total distance away is 1 plus 1/12 times 120. So his distance away is 11 meters. Now, if we want to figure out what the Y value is, and I think I'm just going to go on to another slide here. Put this here. So I know that my X is going to be 11 meters and my dx dt is 120 meters per minute. I don't know my Y, but we'll figure that out. Dy dt is what we are looking to find. So now if we know that he is now 11 meters away, he's 1.8 meters tall, the lamppost is 3.3, now I want to find my Y. I need to use similar triangles here to figure out what the Y distance will be. So we can figure that out. How long will his shadow be at that time, which we might need. I think we might. So I'm going to say that 3.3 over 11 plus Y equals 1.8 over Y. Looking again at those similar triangles, the big triangle on the outside and the smaller triangle inside. If I cross multiply here, I get 19.8 plus 1.8y equals 3.3y, bringing the 1.8y over and subtracting it from the 3.3. I get 19.8 equals 1.5y. And dividing out the 1.5, the y would be 13.2. So that's how long the shadow would be at that time, 5 seconds after he started walking. Now I'm going to kind of take these triangles again and sort of do the same thing but this will help me set up my related rates. So I know that this is x and y and 3.3 and 1.8. And I know that 3.3 over x plus y equals 1.8 over y. And I'm going to, and I just realized I did not need to solve for that y value. So this is one of those ones where you don't always need to find all of the variables. So what I'm going to do here is just cross multiply this and clean it up a little bit before I take the derivative. So 3.3y equals 1.8x plus 1.8y. Bringing the y's both to one side, we get 1.5y equals 1.8x, which is way simpler and is not going to need either of these. So this is my relationship, 1.5y equals 1.8x. Now, that's always going to be this relationship between the two. If we take these two, now we can do the derivative of this, and what we're going to want to find is the dy dt. So taking the derivative of the left side of 1.5y, that's 1.5, and the derivative of y is just 1, and y is a function of time, so dy dt. Same thing on the left, 1.8, derivative of x is just 1, but x is a function of time, dx dt. So here, 1.5 dy dt equals 1.8, and dx dt is 120. So here, dy dt, I'm going to take that 1.8 times 120 and divide out the 1.5 from the left, and we get 144 meters per minute. The last example is kind of a really interesting 3D picture. So we've got a railroad bridge over a river. So there's a bridge like that, and there's a river underneath it. And here comes Mrs. Cooper's terrible drawings. So we've got our bridge like that. Now there is a train. Let's color code this. The train is up here, and it's traveling over the bridge, and it's traveling 60 kilometers per hour. And they are passing over a person in a boat. What color should our boat be? Maybe the boat's yellow. And the person in the boat is traveling 20 kilometers per hour. And we want to know, how fast are the two people separating? How fast is the distance between them getting bigger after 10 seconds? So what we're going to have here, this is kind of reminiscent, I think, because there's a 20-meter height there. That this really feels to me like a 3D vector situation. Remember when we did the distance in 3 dimensions and how it was like x squared plus y squared plus z squared? What this really is, I'm going to kind of say that this is like my just kind of arbitrarily x, and that's my y, and that's my z. So this is like my y and my z and my x, and what we really want to find here is that 3D distance from one point, like diagonally through the box of those 3 dimensions. And I'm going to say that d squared is x squared plus y squared plus z squared. So that comes from what we did with vectors. If you want to kind of take a look back, that would have been when we were doing our 3D algebraic vectors. and looking at the distance between 2 points or the magnitude of a vector. So that's the equation that we're going to use. And the one kind of nice thing here is that z is not a variable. So z is just equal to 20. That is not going to be changing. So here I'm going to simplify this equation and say that d squared is x squared plus y squared and plus 20 squared, so plus 400. And that's going to make this a little bit easier. So a couple of things that we're going to need is that we will need our 3 variables here. I've got d, and I want to know dd dt. I'm going to have to figure out x, dx dt. Okay, last one, and then we'll also have to figure out what our y is and dy dt. Now, the big issue here is that we have our time is in seconds and our bridge height is in meters, but we're given this 60 and 20 in terms of kilometers per hour. So I'm going to change 60 kilometers per hour into meters per second. So we're going to change from kilometers per hour. Changing kilometers to meters, we know that we'd multiply by 1,000, and then changing hours to minutes is divide by 60, and minutes to seconds is divide by 60 again. So if I do 60 times 1,000 divided by 60 again, I get that that's 16.67, and I'm okay with rounding that to 2 decimal places, meters per second. Same thing for the 20 kilometers per hour. I'm going to multiply by 1,000 to get meters, divide by 60 again to get seconds. And that will be 5.56 meters per second. So that's what my dx dt is a smaller one, so 5.56 there, and dy dt is going to be that 16.67 meters per second. We can figure out how far the boat and the plane respectively have gone in 10 seconds just by multiplying their speeds times 10. So the distance that the boat would have gone will be 55.6 meters, and the distance that the train would have gone would be 166.7 meters. Oh, do not delete that. So that x is 166.7. Now we can use those just to kind of save space. I'm going to sub those in just on my calculator to figure out what the distance would be. So I'm going to take this x and this y, just put it all into the distance formula and figure out how far apart would they be. So 166.7 squared plus 55.6 squared plus 400, and then do the square root of that, and the distance between the boat and the train would be 176.86 meters approximately. So this is all just kind of preliminary work. We haven't actually even done any derivatives, but the derivatives are really the easier part. So I know I've got this equation here, and I'm just going to need to make a second slide. So I know that d squared is x squared plus y squared plus 400, and I had my values for d, x, y, and dx dt and dy dt. So I'm just going to do the derivative of all of these, remembering that d and x and y are all just functions of time. So derivative of d is 2d times keep putting a T there, dt, which looks kind of weird, but it's okay. And derivative of x is 2x, but x is a function of time, so that's dx dt. And then derivative of y squared is 2y times dy dt. And derivative of 400 is just 0. So I'm going to put in all of these values. I'm going to have to go back and forth a lot because I don't have my second device out right now. 176.86 is my distance. And that's equal to 2 times x, which I think was the 55. Oh, yes, these guys I wrote in backwards somehow. That will matter. This is 55.6 and this is 166.7. So x is 55.6. And dx dt was 5.56, and then 2 times y was 166.7, and dy dt was 16.67. So multiplying all of these out, I get 353.72 dd dt equals, and multiply the other side. That's about 6,176. So I get that they're separating at about 17.46 meters per second. So therefore, the boat and train are moving apart at a rate of 17.46 meters per second after 10 seconds. So that's how fast the distance between them is increasing. That one is pretty tricky for sure.